Hello, my name is Robert Smith, and I'm with New River Community College's academic assistants. And today we will be working through some of the ideal gas equations. They're all derived from one equation, which is PV is equal to nRT. That is, pressure times volume is equal to the moles times the gas constant times the temperature. Temperature is always given in Kelvin when using these gas laws. So whenever you're given a problem wherein the temperature is provided in Celsius or Fahrenheit or Rankine, you'll want to convert to Kelvin. More often than not, it'll be provided in either Kelvin or Celsius, and then you just make the adjustment accordingly. So our first question asks us to calculate the pressure exerted by 2.81 moles of gas in a container of volume 4.53 liters at 56.9 degrees Celsius. So when we do this problem, we're going to first want to convert our Celsius to Kelvin. So we take our 56.9 plus 273.15, and that gets us 330.1 Kelvin. That's our temperature. The other units that you'll want to keep in mind when dealing with this, especially as it relates to the gas constant, as you're doing adjustments to the ideal gas equation, you may not have to worry about this as much, but whenever you have this R value, this gas constant, you'll want to have your temperature in Kelvin, which should be the case no matter what problem or what equation you use involving the gas problems. But you'll also want to make sure your pressure is in atmospheres and your volume is in liters, because the R constant is given as R is equal to 0.0821 liter atmospheres per Kelvin mole. And in order to get everything to cancel out properly to get your desired value, you'll want to make sure that all of your units match those units provided in the gas constant. Getting back to our problem, we now have the temperature in Kelvin, and we're looking to calculate the pressure exerted. So that means that we're going to want to isolate pressure in our ideal gas equation. To do that, we simply divide by volume to both sides, and we end up with P is equal to nRT over V. Pressure is equal to moles times the gas constant times temperature divided by volume. And at this point, we can simply plug in the values. So we could say that P is equal to 2.81 moles, which is provided in the problem, times the gas constant, 0.0821 liter atmospheres per Kelvin mole, and then multiply all that by 330.1 Kelvin for the temperature, and then divide that whole portion by the volume, which is 4.53 liters. When you do the arithmetic out, you will find, we're going to put it over here, pressure is equal to 16.8 atmospheres. If the problem asks you to give that pressure in something other than atmospheres, you would have to do your conversion in order to get that. Again, we're keeping it to 3 significant figures because 3 significant figures are the least number of significant figures when going through the multiplication and division. It's shown in both the moles and in the volume. And you'll note when you go through this problem that your moles and moles cancel each other out. Your Kelvin and Kelvin cancel each other out. And your liters and liters cancel each other out. And that's why we end up with atmospheres. So you can definitely think about this as a sort of dimensional analysis in its own right. The next problem we have addresses something slightly different. It's asking us to calculate the volume occupied by 4.70 grams of CO2 gas at STP, or standard temperature and pressure. We're not going to use the ideal gas equation. We're simply going to look at what is provided. Whenever they are looking for the volume and only provide either moles or mass, and they say that this gas is at STP, and especially if they say that the gas is acting as an ideal gas, although sometimes it will not say that, and as in this case, it did not say that, we can often interpret this as behaving as an ideal gas. And ideal gases, as you know from your book, have a volume of 22.41 liters per mole. So ideally, gases that behave as ideal gases have that much volume for every mole of gas. Assuming that, we can then calculate our volume by simply saying that volume is equal to 4.70 grams times 1 mole over 44.01 grams, which is the molecular mass of CO2, and we just manipulated it. You could just as easily say 4.70 grams divided by the molecular mass of CO2. But in this case, I like to keep it as a multiplication so that the units cancel out very nicely. And then we just use our identifier of 22.41 liters over 1 mole. 22.41 liters per mole. Going through, grams and grams cancel each other out, moles and moles cancel each other out, and we're left with liters. When you do the arithmetic out, you will find that the volume of this particular sample of CO2, the 4.70 grams of it, should take up 2.39 liters. Let's work through another problem. Each one of these problems, as you probably can tell, is a little different from all the others. And they're using different equations and different properties of ideal gases. This next one says a helium balloon has a volume of 0.44 liters at 1 atmosphere. The balloon is let go and is allowed to rise, and the pressure is then recorded as being 0.50 atmospheres. If temperature remains constant, what is the new volume? Our key phrase is that the temperature remains constant. Whenever you see that something is being identified as being constant, it's going to be a variation on the ideal gas equation. If you recall, Boyle's law specifically states whenever temperature is constant and whenever moles are constant, which we know just by the fact that this sample of gas, helium gas, is encapsulated in a balloon, then when that occurs, the pressure and volume of the sample prior to the change is equal to the final pressure and volume. So P1 times V1 is equal to P2 times V2. It's Boyle's law. The easiest method of dealing with any of these gas equations, because there are multiple variables of similar units involved, is to go ahead and list out your given values. So let's go ahead and do that. We know that volume 1 is 0.44 liters. Our initial volume is 0.44 liters. And our initial pressure is 1.0 atmospheres. So we can write those out. V1 is equal to 0.44 liters. P1 is equal to 1.0 atmospheres. And then we're also given our final pressure, what I will call P2. P2 is equal to 0.50 atmospheres. Now you could just as easily put it as P initial times V initial is equal to P final times V final. I've just used 1s and 2s. You can use I's and F's if you want. So we know what we're trying to find. We know we're trying to find our V value for the final. So we'll have to manipulate our formula to reflect that. In order to do that, we'll have to divide both sides by our P2, or otherwise known as P final. And when you do that, you'll find that your final volume is equal to your initial pressure times your initial volume all over your final pressure. And then all you have to do is plug in the values that you've determined, and your results will be your final volume. So our P1 was 1.0 atmospheres times V1, which is 0.44 liters, all over P2, which is 0.50 atmospheres. And note that atmospheres and atmospheres cancel each other out, and we're left with liters. And our final value is 0.88 liters. And it's worth noting that when you halved your pressure, you doubled your volume. That has to do with the relation between pressure and volume. Let's look at the last problem. If air in a steel container is exerting a pressure of 2.10 atmospheres at 17 degrees Celsius, what pressure does it exert at 86 degrees Celsius? So it's air in a steel container. It's contained, and the container is steel. The fact that it's contained means that we're probably looking at a constant with moles. And the fact that it's steel would seem to indicate that our volume will remain unchanged. This is further evidenced by the fact that they do not give us the volume nor the amount of moles. So we're going to have to deal with something that just involves pressure and temperature. Well, that's relatively simple as well. The equation when volume and number of moles are constant is P1 over T1, or P initial over T initial, is equal to the final pressure over the final temperature. Again, we'll want to convert all of our temperatures to Kelvin because Kelvin can be related to itself very easily. The difficulty in keeping things in Celsius is because the conversion between Celsius and Kelvin is a summation conversion rather than a product conversion. So it would be difficult to accurately portray that because these equations were designed with Kelvin in mind. So if you do it with Celsius, it will be wrong. Having said that, let's go ahead and put down temperature 1, or temperature initial, is 17 degrees Celsius, but we're going to want to convert that to Kelvin. So 17 plus 273.15 is equal to 290, accounting for our significant figures. Our initial pressure is equal to 2.10 atmospheres. And our final temperature is equal to 86 degrees Celsius, which means we're going to convert that to Kelvin, which would be 359 K. Now, if you were given a different unit for pressure, like kilopascals or millimeters of mercury or torrs, because their conversions are based on multiplication, there's a direct proportionality to them. So you could theoretically leave those alone. So as long as it doesn't ask you for something in a different pressure, and let's say the 2.1 atmospheres was given in kilopascals, you could leave it in kilopascals and your answer could be in kilopascals. But because we're given atmospheres, let's just keep it in atmospheres. So we're solving for P final. And in order to do that, we multiply by our final temperature to both sides, and we get P final is equal to P initial times T final times T final all over T initial. And that gets us 2.10 atmospheres times 359 K all over 290 K. And when you do the arithmetic out, you end up with 2.60 atmospheres. So these were just a couple of problems that utilize the ideal gas equation and variations thereof for you to practice with. Just remember, whenever dealing with the ideal gas equations, you'll want to convert your temperatures every single time to Kelvin, no matter what the other unit is. Even if they ask for the temperature in Celsius after the fact, you'll want to convert to Kelvin and then convert back to Celsius after you've done the calculation. And that's imperative due to the relation between Celsius and Kelvin. All the other ones, pressure and volume, you could just leave those alone. They can be, as long as you're not dealing with the ideal gas law in and of itself, you can theoretically leave them in whatever units. You can leave, if initially you're given a volume of milliliters and they want the new volume and they don't specify whether it's liters or milliliters, you could leave it in milliliters. Only if they specify should you change those, but you do need to change temperature 100% of the time to Kelvin.